Hello everyone, I am Özge from Technical University of Munich, and today I am very glad and honored to be invited in this session to present my work on Copula mixture models and clustering for non-Gaussian data, which got published in Econometrics and Statistics in this year. And it is a joint work with my supervisor, Claudia Chodo. And today I will briefly introduce you to Copulas and mixture models, but I will mostly focusing on the clustering part and our benchmarking studies. So to start with, Copulas are a flexible approach to summarize dependence in a multivariate distribution. Suppose you have a p-dimensional random vector with joint cumulative distribution function f and univariate marginal distributions from f1 to fb. Then by Clark's theorem, there exists a Copula C corresponding to F, which is a multivariate uniform CDF, which separates the marginal distributions from the dependence structure. So indeed, there are many standard Copula families, but they cannot accommodate asymmetric tail dependence in the data. Therefore, to make them more flexible, Copulas are proposed and built out of bivariate copulas glued together by conditioning ideas, and their building plan is given by a line tree structure. So let's look at the figure 1 that we see the three-dimensional line tree structure. So you can imagine as if you have a three variables in your clustering problem. And this line tree structure models the dependence between the first and the third variable and the third and second variable. And then in the second tree, it models the condition of dependence between first and second variable given to the third variable. And each dependence, for instance, each edge can have different dependence structure. For instance, there can be symmetric dependence here and asymmetric tail dependence here. Therefore, such flexibility can be extended and combined with the mixture models. So we are saying that why not to select the density for a hidden component in the data by Copulas and propose a Copula mixture models. So in the equation 1, you see the general formulation for a finite mixture model. So what we are doing to express each component into the data, the J with a specified by a Copula. Of course, there are many selection and parameter estimation problems to make the life a little bit easier. First, we are starting with the assumption of the known total number of components. And then what we are proposing is a data-driven approach to the remaining model selection problems. So which includes also using the different initial partitions to estimate the initial parameters. And then we are adopting a expectation conditional maximum, meaning the ECM algorithm for the parameter estimation. Now, I will more details and their estimation problems are into the paper, and I am directly jumping into the clustering parts because at the end, now we have a finite mixture model framework with a Copulas, and that we can use in a model-based clustering just by assigning to the highest posterior probability of a given observation to its cluster. And what we did mainly in the paper is first of all to compare to the clustering quality of our methods with a competitive distance-based clustering algorithm K-means, for which data is normalized, and we use the misclassification rates. Why we use K-means as a comparison is first of all, it is a well-known algorithm, and also it is the algorithm that we use to initialize our algorithm. And therefore, it is important to see, for instance, how much improvement our algorithm is giving compared to where it starts. And then we are making a comparison with other model-based clustering approaches, like mixture of normal distributions and scale mixtures of skew normal distributions, which includes multivariate skew T, skew normal, and also the multivariate T, using the mixed SMSM into the R package based on the BIC and the misclassification rates. And why we are using this R package and specifically, by the way, is that they are also using the K-means as an initial partition and to initialize their parameters. And then their stopping criteria to estimate the parameters is to stop if the number of iterations in their EM algorithms is reaching out to the hundreds. So therefore, it is initialization and stopping criteria is similar to us, making a kind of more fair comparison. And then we are analyzing our algorithm's sensitivity, stability, and some computational costs. And to make the algorithm available for everyone and to make the simulations replicable, then we are also providing its R package in the called line class. It is currently in GitHub, not in Cron, but it can be used as a pure R package using the link under the GitHub. So to make a benchmarking analysis, we also use 4 different data generating process. And in all of them, we have 3 variables, 2 clusters with novel labels so that we can compare the accuracy. So we have either 100 or 500 observations in each cluster, allowing us to test out the different number of observations. And we replicate our process 100 times. To give an example, in the first and in the second DGP is just coming from a mixture of wine copulas. So here I give an example, but what is the main message here is that the dependence structure is different in each cluster that we simulate from. So for instance, in the first cluster, the highest dependence is between first and second variable. In the second cluster, the highest dependence is between first and third variable. And there are asymmetric tail dependence, or there are between some pairs of variables, and there are some heavy tails margin. So it is it is true for the first data generating process. In the third one, we are simulating from a mixture of multivariate normal using the wine copulas because we can express it. And in the fourth, the last scenario that we are using a misspecification scenario, then we are using a mixture of multivariate skew test distributions to test our methods also in misspecification scenario. So to start with, in the first data generating process from a mixture of wine copulas, we see that our algorithm improves to the accuracy more than 20% compared to the k-means for this non-Gaussian non-elliptical data. So on the left plot, we see the results for 500 observations. And on the right, we see the results for the 100 observations, and we just use the misclassification rates. So we see, first of all, like the VCMM is always better than the k-means in both scenarios, but the variance for both algorithms as the sample size decreases is increasing. And also, on average, VCMM's misclassification rate is worse with the smaller sample sizes, but k-means is more stable, being independent of the sample size, which is normal because in the wine copula mixture models, we need many parameter estimation and model selection, which needs more data to be more stable. And in the second data generating process, again coming from a mixture of wine copulas, we see, so on the, if you look at the top left plots, we see the 2 components, green and red, and there are some tail dependence and heavy tail margins. So let's first look at the mixture of multivariate normal distribution fit on the bottom left. You see, so if you focus on the scatter plots of X2 and X3, so compare it with the original, the true labels, you see that it cannot capture the observations on the tails. So if you fit on the bottom right, the mixture of multivariate security, you see it is better than the mixture of multivariate normal in terms of misclassification rate and the BIC, but still it has problems on the tails. So because there are different tail dependence structures, so it's not the same in each pairs of variables. So however, if you fit the wine copula mixture models, you see these observations on the tail are better captured, adequately captured. So of course, we again replicate our process 100 times for 500 and 100 observations. And in each of the plot, in each of the box plots in the first columns, that you see our algorithms is better in terms of BIC and misclassification rates. And after that, we see the multivariate skew, the mixture of multivariate skew distributions like skew normal and skew T is better than the elliptical distributions, multivariate normal and multivariate in terms of the BIC. However, the BIC is not matching with the misclassification rate because multivariate skew normal is worse than the multivariate in terms of it, but it is just showing that the BIC, so to estimate the density of the data, in such kind of situation with heavy tail margins and tail dependence, after the VCMM, this mixture of skew distributions are better. In the third data generating process, it is coming from a significant overlaps among the components and coming from a mixture of multivariate normals. But here you can see the shape of the data is a more kind of X shape. And we were suspecting that if we are starting with a k-means, maybe we may not recover the true parameters and the true model components. And if, as we guessed, our classification accuracy is just stays with 65%, but when we change our initial partition, it goes up to 95% and with a better BIC value. And as the data generating process, if we fit the mixture of multivariate normal distribution, classification accuracy is around 96%, and with having the best BIC compared to the other VCMM. And in our last data generating process with the specification using the mixture of multivariate security, you see in the table the misclassification rate and the average BIC using the multivariate security is the best, but our algorithms is better than using the multivariate normal in such situations, because the mixture of multivariate normal distributions has more difficulty in capturing non-elliptical components than our methods. So this was the adjusted simulation studies, and we have also 3 more real data set analysis to make more comparison in terms of the clustering quality and also in terms of the computation time. But I will just focus on one real data set that we analyze the stability of our algorithm to select the optimal number of components, because based on the BIC, because we see that it is changing by the starting partition. So we start analyzing the SAX protein data, which contains continuous logarithmized levels of 11 proteins in individual sets, which was subject to some chemical interventions to learn the causal pathways linking a set of these 11 proteins. So this data set is a kind of state-of-art data sets in the causal analysis in the Bayesian network. And there are some works that fits, for instance, like 2-component Gaussian mixture Copula, and which is showing a better, let's say, fits rather than assuming just one multivariate distribution, but it is not clear how many components or are there any components in the data. Therefore, we decided to fit our algorithms, just start initializing it by k-means or with a model-based hierarchical clustering, and just using the number of components from 2 to 11. And what we see is that if we start with k-means, then the optimal number of clusters is 9. But if we start with the hierarchical clustering, then the optimal number of clustering is 10, meaning that the number of component selection is not stable. And here is a summary of our main contributions, and I'd like to thank you for your attention and time.